Hi, welcome in. So we want to be able to prove the derivative of basically a power function here. So I've kind of shown two power functions. Okay, so one is with positive exponent and then one is with the negative exponent. You can tackle them in exactly the same way, and I want to just be able to show you how the derivative itself of any of these power functions, so if you take the derivative, how it is just simply equal to the actual exponent, which comes to the front, and then multiplied by your variable, your x, and then you're just subtracting 1 from the exponent. So that's going to be our goal. Now, if you are working with the negative exponent, so it's going to be exactly the same thing. So that negative n would come to the front. Then you have an x, and then it's negative n minus 1 that you're going to get up on top. So that's what we're going to be showing, that is actually the derivative. Now, knowing this derivative is, of course, super useful. Where does the actual, proving come from? Well, it comes from the original definition. So if you recall, you will take the limit as h is approaching 0 of any function. So this would be x plus h. So we substitute the h in there, we added. So we're basically creating a little bit of a secant in here in between 2 points on the graph. And then we have f at x, and then all over the h, and then as h approaches to 0. And the biggest problem here, if you have studied limits, you'll know that this particular limit will always give you indeterminate if you try to just do it by simple brute force, because you're going to get fx minus fx, which is 0, and then over h, which is approaching 0, which is 0. So from this definition, let us take the first, so this function, and then I'll come back to the negative. You'll see that it won't be any different. You'll be able to follow the same procedure. Now, if I substitute this in here, so I'm gonna just drop this limit for the time being. We know that this is approaching 0, so we'll get there. So I'm just gonna take the actual difference up on top. So if I substitute into the difference, I'm going to get x, this is gonna be plus h to the n minus, and this is gonna be just x to the n, and then this is all going to be all over h, right? And then as the limit is approaching, so as h is approaching 0 in the limit. Now, the ultimate trick with this is that you notice that the limit definition right here is basically a difference, right? So for all of you who may not remember, we can utilize a trick in here to be able to help us along to be able to solve this, because we have to massage this along the way to be able to find this actual derivative all the way up on top here. So here's the trick. I mean, it's not a trick. The only thing is that you have to remember what the difference, if you may recall, so difference of squares, difference of cubes, and then you want to take the general difference, of the nth degree. So in that difference, what it states is, it states the following, that if we have an a squared minus b squared, or whatever those variables are, this is nothing else but simply the factored form is a minus b, and then the other factor, so it's an annoying factor, and I'm sorry here, so this is the general case, so I'll put to the n here. So in the general case, what will happen is this will be a, and then this is going to be now n minus 1, and then all of these terms now are going to be positive. So this is a n minus 2 to the b, plus this is going to be a n minus 3 to the b squared, plus, and then this just continues on until eventually you are basically running into, so I'm just going to shorten this up for us. So this is going to be a to the n, and then this is going to be b n minus, I guess, 3, okay, plus a to the 1. And then this is going to be b n minus 2. And then finally, this is going to be b n minus 1. So now, remembering this, I actually showed this. I did a video exactly on the difference of squares, cubes, and the nth degree all in one video. I'll put up a link up above there if you want to see that proof. Now, why do we need this particular trick is because we have an nth degree here, difference actually, in between. And you can think of this right here as, your A, okay, and then you can think of this as your B. So what I'm going to be doing is I'm going to be kind of factoring this out. So if I factor this whole thing out, then what I will have is the following. I'm going to get x plus h, all right, minus x. Okay, so that is this term right here. Now, once I have this, okay, now I'm going to take, this big long term. Okay, so just bear with me. So within here, so I'm going to get x plus h raised to the n minus 1. So plus, this is going to be x plus h raised to the n minus 2 times your x, okay, to the 1 plus, now I'm not going to write all of the terms in here. I'm going to put dot, dot, dot until you eventually get to the, let's say, the last two terms, which are going to be x plus h to the 1. And then this is going to be just x minus 2. And then I'm running out of space there. So plus the last one, which is going to be x n minus 1. And then that's all in brackets. Now, why does this help me? Well, this helps me because what I have now is, notice that this x, okay, minus the x, okay, this is just going to have an h in front here. So I'm going to have h, all right, and then multiplied by, now all of this junk, okay, so multiplied by all of, all of these things in here. So I'll just write it as a bracket in here. I'll put a tilde, so that's all of that. I just don't want to rewrite it. And then, of course, this was all over h. Okay, so if I'm going to be putting this over h, okay, like so, now notice that the h and the h cancels. And now what happens is that we can actually apply the limit. Okay, so this entire thing that I have in here, so this is, as limit h is approaching to 0. And therefore, you really only have that bracket. But having that bracket, you can now use the limit properties for every single term. So what you're really having is all of this is gone, and this is going to be limit as h is approaching to 0 of the first term. So this is going to be x plus h, right? So n minus 1 plus, now I'm bringing in the limit inside because I can do that by limit properties. If you don't remember the limit properties, I'll put up a link up above there. It's another calculus kind of item. So I have that, and then this is going to be the next one. So this is x plus h, n minus 1, x1 plus, and I'm going to put dot, dot, dot. I don't want to be rewriting all of these. I think you get the gist. Now, as h is approaching to 0, so you'll notice that, this one is gone. So really, this limit is nothing else but x, and then this is going to be n minus 1. Now this right here, so plus, again, okay, so my h, so this h in there is going to be approaching 0, so it's basically 0 if we take in the limit inside there. So this is going to be just, I'm going to write it up above there, x to the n minus 1 times x to the 1, okay, and so for that, so I apologize, this should have been a 2. Okay, I just didn't copy this correctly in here. So when you do that, now you're going to get, okay, so this is 2. So this whole thing is, again, nothing else but x n minus 1 plus, and then, it's going to be happening the same thing as you bring in the limit inside of all of those. So the h's will just be going into 0, and then you'll just have a bunch of terms, okay, that are x n minus 1. Now, how many of those terms do you have in here? So you can count them up, okay? And you'll notice that you actually have n of those terms. So in total, okay, in that bracket, you have n of those terms. So if I have n of these terms, so n terms that are the same, then this is nothing else but simply n, okay, x and minus 1, because you're just adding them, you're just adding like terms together. And that is the actual derivative, which is exactly what we wanted to show. So that is the proof, okay, of having this right here. So that's pretty neat. Now let's take a look and see, what would have happened if we had fx is equal to 1 over x to the n. Okay, so if we have this, which really is just x to the minus n, okay, like that. So I'm going to use the same trick, okay, as I have used above here. Now it is a little bit more work, okay, so let's take a look and see, so you can just bear with me. So I'm going to start again, so with the definition, so limit as h is approaching to 0. Now if I substitute that in here, so x plus h, and this is going to be negative n in there, minus, okay, this is x minus n, okay, all over h. All right, so for the moment, let me just drop this, okay, and then I'll drop this as well. I'm just going to be working with the actual numerator to try to simplify things for you and then show you. So the first thing is that it's not exactly the nth difference as I had above, because I have that negative, but that doesn't cause me much headaches actually, because what I can do is I can say the following. I can say x plus h. So this, if you know your exponent rules, okay, so this is the same thing as that. Then minus, this now is going to be x, and then this is to the negative 1. And then I'm going to bring that n outside in there. Okay, so that's my new numerator. So now with this, okay, so notice now I do have the nth difference. So here's the difference in between them. So I can factor this out. Okay, so this is equal to, and it's going to be this, okay, minus that. So I'm using exactly what I did, okay, so right here, I'm just using that, okay, except my a now looks a little funky, okay, so this is my a right there, this is my b right there, so I'm going to have x plus h to the minus 1 minus x minus 1, so that is the factor. Now, the annoying part is, I have to come up with all of this junk, so be it. So just bear with me. I'm going to just do that in fast forward fashion to write out those particular terms. All right, so here we have it. Those are all the different terms that I have. They don't look too pretty, but again, just think about it. Okay, so this is really just your A, right? So this is your A, and this is your B. All right, so this is your A, this is your B, and this is your B. So it's exactly the same thing. I'm just using the difference of the nth degree here. Now, what is a little bit, it's not as nice as the previous case is, so right here, so if I simplify this out, I'm actually going to write it out as numerators and denominators. So this is what this equals. And so if I simplify this, it's going to be x minus, I guess, so it's going to be x plus h. So I'm finding a common denominator here. So that's going to be x plus h, so that's that. I'm not going to worry about all of this junk on the right-hand side for the moment. So within here, so then this is x minus the x, and then minus, so it's going to be negative h, all over x plus h. So that's what I have right there. And then, I have all of this junk, okay, in there. Okay, so all of that. okay, is going to get put into the air. I just don't want to rewrite it again. So I'm just going to keep it for the moment. And now, so bringing everything back, so don't forget, so this is over h, and we're taking the limit as h is approaching to 0, right? So, you know, this h is going to cancel this h out. And as h is approaching to 0, then, you know, this whole thing, so I have a -1 on top, because that h canceled. And in the denominator, I have, now h is tending towards 0, so this is 0, so this is going to be x times x, so this is just x squared. So that's what I have in here. Now, inside of this bracket, right there, as h is approaching 0, so all of these different terms, so notice what I'll have. Maybe I'll write it up above there, okay, just so that you can see it. So let me write here, and then I'll use a different color so that it pops out for us. Okay, so the first one is, so this right here, as h is approaching to 0, what I'm going to get is, so that h is 0, right? So this is going to be x to the -1, all right? And this is going to be n minus 1. So that's what this will be, plus, okay? Now again, so this is h is approaching 0, so I'll have x to the -1, and this is n minus 2, times x to the -1. So that's this term, now this term, plus, right? So now we're just doing the same thing all the way throughout. So we have, you know, dot, 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 and then, you know, so all of these, once again, I'm going to get just x, this is 0. So x to the -1, and that's going to be just to the 1, multiplied by, so this one, x to the -1, and this is n minus 2, plus, and then this is x to the -1, n minus 1. So once again, what you notice is that what I'm having, okay, in all of these cases is I'm going to have n terms. So if I simplify all of these, okay, this is just going to be x to the -1, right? So those are my terms, x to the -1 to the n minus 1. And how many of these do I have in here? Well, I have n of those terms in there. So that's what I will have right there, right? So in here, so this is n x minus 1, n minus 1, all right? So now, okay, so negative, and then the n, so this is going to be -n, okay? And then in the numerator, so I have x, okay? So this is now going to be, I'm going to bring this, you know, so this times that, so that's going to be a negative, okay? So this is negative n minus 1, so if I multiply that through, and this is divided by, so that x squared there, right? Now, your exponent rules, so I'm doing division, so this is negative, maybe I'll just keep it all in 1, so -n, I'll bring this inside here, so plus 1, and then minus the -2, so this is going to be -n, and, you know, this is just -1. So in total, I have -n x to the exponent of -n minus 1. All right, which is exactly, so that is the derivative that we were looking for. Okay, so that proves that fact. Now, you know, you can write this in many different ways. This is -n, you know, it's the same thing as just simply, you know, if you bring that in there at the bottom, this is going to be x, okay, and I guess it's going to be plus 1, right? So you can write it like this. You can, you know, write it -n, x negative, and then this is n plus 1, whatever. These are all exactly the same. So now you have the proofs for your power functions, both positive or negative. All right, so I hope that you found this useful. I think it's a good exercise for yourself to be able to see this. You know, in grade 12, if you're doing this or if you're starting, you probably are just going to remember the rule of the derivative, but now you can see kind of where it comes from. Thanks for watching. See you in a future video. Bye, everybody.